I'm going to give you some tips for PostLab 5 measuring Ka and Kb. The first problem is just going to contain data from the lab. You will have recorded the molarities of all three of these solutions and then also the pH values of all three of these solutions. In question number 2, you are going to use the pH of the HCN solution to calculate its hydronium ion concentration. And just as a reminder, the equation that you want to use for this calculation is H3O plus equals 10 to the negative pH. So you're just going to be plugging in your pH value in this particular spot. Then you're going to create an ice table for HCN. Now, as you know, in the ice table, the initial molarity is going to be the molarity from the bottle. Let's just say that it's 5. It's not 5, but let's just use that number. And then, as you know, we don't need to fill in any data for water, and the initial amounts of the products are always at 0. Normally in an ice table, we'll go like this, minus x plus x plus x, and then we'll go 5.0 minus x, x, and x. In this situation, you actually know the H3O plus concentration because you calculated it right here in problem number 2. Let's just say that that ended up being 2. So instead of writing x here, you can write 2. Now, mathematically, x is equal to x, so everywhere in this ice table, everywhere that you have an x, you can replace that with whatever your H3O plus concentration is. I'm just doing it like this. Again, this is not what your data is going to look like. And actually, for this one here, we can actually just work the math out on that. That's going to be 3.0. In question number 4, you're going to write an equilibrium expression. This is going to be Ka. You're going to have products over reactants like you normally do. And what you're going to do is plug the numbers in from your ice table, plug them into this equilibrium expression, and solve for the value of Ka. Then you're going to do pretty much the same thing with the NaCN solution that you did in that you used in part 2. This one's a little bit different because it's a base. So we have to start by converting the pH to the pOH for the solution. And as a reminder, the pH plus the pOH is always going to be equal to 14. So you'll be able to plug the pH value in that you got from the lab and use that to solve for pOH. Once you know the pOH, you're going to use that to calculate the hydronium or the hydroxide ion concentration. That's going to be 10 to the negative pOH. And with that information, you're going to make an ice table pretty much exactly the same way that you just did. You're going to write in your initial molarity of cyanide. These will be zeros. You'll plug in your OH minus concentration, the one that you just calculated right here. And you'll fill in the rest of this ice table just like you did in this spot. So there won't be any x values. Once you get that all filled in, then you will be able to calculate the equilibrium constant. You'll write up a Kb expression because this is a base. And you will plug the numbers in from this ice table into the Kb equilibrium expression, and you'll solve. Now for the third part, the Hcl solution, this one's going to be a little bit different. You are going to use the pH to calculate the hydronium ion concentration, 10 to the negative pH. Then you are going to create an ice table. And in this ice table, we're going to start by filling in the initial molarity of HCl. Let's just say that it's 5. And we're going to use the ice table to predict the value of H3O plus. So we're not going to do what we did in the previous problems where we took this number and plugged it in down here. Instead, we're going to use the ice table because this is a strong acid. That means, by definition, that means that it reacts completely. So whatever the initial molarity is, that's what our minus x plus x value should be. And because this is a strong acid, at the end, we should have 0 HCl. And we should have a full reaction, and whatever initial molarity we had for HCl, that's what the final molarity of H3O plus would be. So what you're going to do is compare the H3O plus value that you got from the ice table, compare it to the H3O plus that you calculated from the pH. And answer this question. So after you compare them, are they the same? Are they really similar? Are they significantly different? Does your data, so this is your data, the pH value is your data, does your data support the claim that HCl is a strong acid? If HCl is a strong acid, you should have 100% of it being converted into H3O plus. So let's just say when I did this, let's say that my H3O plus calculation that I got was like 1.2. That would mean that my prediction would be that I would have 5 molar H3O plus, but it turned out I only had 1.2. So that would mean if this was my data, if this is what I was comparing, I would say, no, those are pretty different. And so that means that HCl is not completely dissociating the way that I would expect it to. It's only partially dissociating, and that does not support the claim that HCl is a strong acid. If these two numbers end up being exactly the same, they were exactly the same, or even if they're really similar, like maybe I get 4.8, that's pretty close. If these two numbers are pretty close, then I would say, yeah, that probably means that HCl is a strong acid. It seems like it's behaving like a strong acid because these numbers are really similar.